All right, so this is the solution to Kuklin's example problem, problem 3 from the example exam. So this is very similar to the example problem 6.2. The only difference that we see here is that this conducting bar is at an angle, and the B field is also at an angle here. So this bar is tilted by 30 degrees, right? And we're sliding forward with this velocity here. And then this B field is also tilted at an angle of 30 degrees. Okay, so we are actually, in this case, we're remembering our cross product and our dot product rules. So if I have A cross B, it can also be equal to AB sine of the angle between them, right? And then if I have A dot B, it can also be equal to AB cosine of the angle between them. Okay, so we want to remember these two things for this particular problem because that's how we're dealing with the angles in the easiest way here. Okay, so essentially, if you have a B field, so we have a B field, and we slide a conducting bar through that B field at a particular velocity, we can induce a current. So we're inducing a current in this whole circuit here, and we want to find this VEMF, this voltage. And so what we're going to do is we're going to take this velocity crossed with our B field and then dotted with our DL element. So the DL element will always be along the conducting wire. So this DL is moving along here. So it's in our current direction, essentially. I just didn't draw it in the picture, but it just follows our current. Okay, so what do we need here? Okay, so first off, we're going to do this cross product. So if we have this velocity cross B, we're going to use our cross product rule here, right? And we have U multiplied by B times sine of 30. So the angle between the B field, let me draw it a little bit darker here, the angle between the B field here, right, and the velocity is 30 degrees. So that's why we end up with this UB velocity times B times 30 degrees. Okay, so that's the first part here, right? That's that cross product. But then we also have it dotted with DL. So the DL is our differential, the path that our current takes, right? So we're going across this line. It's this differential line from C to B, okay? And it is so once we do B cross U, right, our resulting vector is going to be, if we remember the cross product, our resulting vector is actually in this direction here. So that's what B cross U is going to give us. And when we take the dot product, so this is just getting kind of really a little dicey with our cross and dot products, but when we take the dot product of this vector with DL, we want to look at the angle between them. And so in that case, that angle is actually going to be equal to 60 degrees because, so this one's 30, right? So this one's also 30, and then this one is also 30, right? If we remember our angles, because this line is connected. So this is going to be 60 here. So that's how we end up with this value over here, where we have our cosine of 60 degrees, because it's essentially this resulting U cross B, right? We have this resulting cross B, and then dotted with DL, which is the line at this angle here, and then the angle between them is right here. So this is the angle between them, and that's 60 degrees, 60 degrees. So cross product first and then dot product second. So that's the result of the dot product, and that's why we end up with this expression here. Okay, so hopefully that part makes sense. If it's not super clear, go ahead and go back and maybe watch that again. But then the rest of this isn't too bad here. So we're going from B to C. So we're integrating along that path there. And then just to find our induced voltage here. So putting all these components together, we can just sort of simplify this quite a bit because we're given a value for our velocity. We're given 5 meters per second. We're given 1 Tesla for our B field, so we can plug that in. And then when we move from C to B across our differential length, let's see here. Are we given a differential length? Oh, we are given a length of BC. It's 1 meter, right? A 1 meter long bar, LCB. So we plug that in, and then we can actually just solve for our VEMF here. Okay, so it also asks us to find the current. So once we find our VEMF, we can just use KCL. So just basically here, I is equal to V over R. And that's going to give us our total current. So hopefully that makes sense. So that's just kind of an overview of how to deal with those angles. It helps to look at the figure and kind of recognize the geometry. These rules for cross products and dot products may help you save some time with this particular expression for VEMF. So if you do have angles there.